I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on electromagnetic induction, magnetic flux, Faraday's law, and motional EMF. In this video, we're going to talk about electromagnetic induction, which is magnetic flux, Faraday's law, also Lenz's law, and motional EMF. So we're going to start with magnetic flux. So if we have a horseshoe magnet, and we look at the north and south pole ends of the horseshoe magnet, and we consider the uniform magnetic field between the north and south pole, and we place a cross-sectional area in that magnetic field that is perpendicular to the field. The magnetic field is going to be directly proportional to the number of lines per cross-sectional area, the number of lines going through that area. Now, if we rearrange that proportion, the number of field lines is proportional to the product of the magnetic field and the cross-sectional area. Now, the magnetic field times cross-sectional area, is known as magnetic flux, which is denoted with the Greek letter phi. And so phi with the subscript of b, that is going to be equal to the magnetic field times the cross-sectional area. Now, the cross-sectional area is also a vector quantity, and the vector for the cross-sectional area is perpendicular to the area in the field, which means that it's parallel to the magnetic field. So this maximizes magnetic flux when the area vector and the magnetic field vector are parallel to each other. So magnetic flux, as we said, is denoted with the Greek letter phi, and the unit is a Tesla meter squared, or also known as a Weber. A Weber is abbreviated with a capital W and a lowercase b. So the word flux is just an analogy for flux in a fluid, which is the volume of a fluid that flows through a cross-sectional area per second. So if we picture a fan blowing air and we hold up a hula hoop, the flux would be the amount of air that goes through that hula hoop, and everything that goes around would not be counted. So magnetic flux works the same way. It's the number of field lines that go through a cross-sectional area. So the more field lines, the more flux. And it can be thought of as a total magnetic effect on a coil of wire of a given area, which we'll discuss in this video. Now, magnetic flux is equal to the magnetic field times the cross-sectional area. And if there's an angle between the area and the magnetic field, since they are parallel and that maximizes it, we're going to multiply by cosine of theta, because if theta is 0, that gives us 1, which is the maximum value that we can have for a magnetic flux. So theta is the angle between the field and the area vector. Now, examples of magnetic flux. So we have a cross-sectional area, we have a magnetic field, and if we increase that magnetic field, we can see that the number of field lines that go through that cross-sectional area increases. So that's an increase in flux. So the stronger the magnetic field, the stronger the flux, and vice versa. The weaker the magnetic field, the lesser the magnetic flux. So another way we can change magnetic flux is by changing the area. So we have a smaller area to a larger area. That just means that we're going to have more field lines going through, so we increase the magnetic flux. And the third way that we can change magnetic flux is by changing the angle between the area and the magnetic field. So when the magnetic field and area vectors are parallel to each other, that maximizes the magnetic flux. If there's an angle, then we have a smaller magnetic flux, as you can see in the example at the bottom of the screen. All right, so we're going to talk about Faraday's law of induction. So we have a coil of wire, and we have a magnet that is brought close to that coil of wire. And we're going to hook up an ammeter to our coil of wire. And to no surprise, there's no current flowing through it because there's no power source. So the ammeter is reading 0. Now, what happens when we move this magnet close and it increases the magnetic flux inside the coil of wire? You can see that there's a negative value of current that is induced from the change in flux in this coil of wire. When we stop moving it, then the current goes back to 0. Now, when we take that magnet and now move it back away from that coil of wire, what you can see is that we now have a positive current. So the current's moving the opposite direction because now we're decreasing the magnetic flux. And again, when we stop moving it, the current drops back to 0. So let's look a little bit further into what's going on and why this is happening. So the change in magnetic field induces a current, and the coil has a resistance of R to the current, and I times R, that's Ohm's law, that gives us the change in potential, or the EMF, and this is known as an induced EMF of the magnetic flux changing. So Faraday's law of induction is that the induced EMF, measured in volts, is equal to the change in magnetic flux based on the magnet moving back and forth over the period of time while the magnet is in motion. So the EMF can be calculated by the change in flux divided by the change in time that it took to change that flux as we move the magnet towards it. Now this gives us the absolute value. The absolute value of the EMF is going to equal the absolute value of the change in flux over change in time. Now we're going to talk about Lenz's law. So Lenz's law, we have a vector that is pointing to the right that represents the initial flux that is through the coil of wire. Now, as we move that magnet closer, we know that the flux increased. So we're going to represent the flux with the vector, in this case, that is longer than the initial. So the change in magnetic flux is going to be a vector that is represented by this black arrow, and that's the change in flux, the final minus the initial. So the final being larger means that the change is going to be in the same direction as the flux. Now what happens is that everything wants to be in equilibrium. The coil of wire wants to be in equilibrium, but the change in magnetic flux causes it to not be in equilibrium. So the coil of wire then induces a current that produces a magnetic field that points in the opposite direction of this change. So we have a magnetic field that's induced by the current in the wire pointing in the opposite direction. So this opposes that change in flux from the magnet moving close to it, and that is why we have a current that flows through the wire. Now, if we use the right-hand rule, we point our thumb in the direction of the produced magnetic field in the wire, and we wrap our fingers around, we can see that the current is going up in the front and down on the back. So it's going from up in the front, down on the back, and this is why it's negative, because when it goes up in the front, down in the back, it goes through the red and then out the black, and that is the negative direction for current. If we switch the wires, it would be a positive, but in this case, the way we have it set up is negative. So in the reverse situation, we have an initial magnetic flux. That arrow is represented by a longer arrow, and the change in flux is going to decrease. So as we move that magnet away, so the change in flux is going to be represented with an arrow pointing to the left towards the magnet. The change in flux then from the magnet being moved away is going to induce a current that produces a magnetic field that opposes this because it wants to be in equilibrium. So that means the magnetic field is going to point to the right. So we can figure out the direction of the current by, again, pointing our thumb in the direction of the magnetic field, wrapping our fingers around, so the current's going to come down in the front and up in the back, which is why it's positive, because down in the front means it's going to go through the black and then to the red to induce a positive current. So when we look at Faraday's law and we combine it with Lenz's law, Faraday's law is the absolute value of the EMF is equal to the absolute value of the change in flux over time. But we apply Lenz's law and it gives us a negative sign because it's inducing an EMF that is negative to that change in flux from the magnet. Now this equation is used for one loop of wire. Now if we have multiple loops of wire, every time it coils around, we'd multiply by the number of coils in that loop, which is the capital N. Now the induced EMF is equal to the negative number of coils in our loop times the change in magnetic flux divided by the change in time. Now to induce an EMF, there must be a change in flux through the coil of wire. So we can change the magnetic flux by changing the magnetic field, by changing the area, or changing the angle between the magnetic field and the area. Now let's look at an example problem. So we have a rectangular coil of wire with a magnetic field directed into the page, and that magnetic field is decreasing into the page. Now, what we want to do is find the direction of the induced current in the wire. Now, we're going to represent this vector pointing into the page, so kind of up and to the right is going to be into the page, and the magnetic field decreases, so that means the vector is going to decrease. So the change in magnetic field is going to be pointing out of the page, which means that the wire is going to have a magnetic field that's produced into the page. So that means if we use our right-hand rule and we take our fingers and point it into the page anywhere inside that loop of wire and use the grip rule to grab the wire, our thumb is going to be pointing in the clockwise direction all the way around that loop. So again, take your fingers pointed into the page, grip around the wire, and your thumb is going to point in the direction of the current. Now, if we put some numbers to this, we have a 5 by 6 centimeter loop of wire, and the magnetic field decreases from 20 Tesla to 0 in 0.2 seconds. And if the loop has a resistance of 10 ohms, we want to find the current in the loop. So we're going to look at the induced EMF equation. And we know that the induced EMF, that number of coils is just 1 because we only have one coil, so we can multiply by 1. And we already found the direction of the current, so we don't need the negative. So we're just going to do the induced EMF is equal to the change in magnetic field times the area. Since they are parallel to each other, the magnetic field's into the page and the area vector's into the page, so cosine of 0 is 1. Now we can substitute in the values that we were given. We know that the cross-sectional area is going to be 0.05 times 0.06, and when we plug in all of our numbers, we get an EMF of 0.3 volts. Now we are asked to find the current, and if we have the EMF and the resistance, well, we can just use Ohm's law. I is equal to the EMF divided by the resistance, plug our numbers in, and that's going to give us an induced current from the changing magnetic field of 0.03 amps in this loop of wire. Now, motional EMF just means that we're putting a conductor in motion. So if we look at our same magnetic field that's pointing into the page, and then we take a conductor and we move it through that magnetic field, what's happening is that the charge in the conductor through the magnetic field is moving. So as the rod of length L moves to the right, we can use the right-hand rule to show that the magnetic force is up on positive charges. So we point our thumb to the right, our fingers into the page, and our palm is going to push those positive charges up or the negative charges down. So that means we're going to have a collection of positive charges at the top and a net negative charge at the bottom. Now, when we look at that, as they continue to move, eventually the charges are going to stop moving and collect with the positive at the top and the negative at the bottom. And when we have the top being positive and the bottom being negative, well, that's going to produce an electric field inside our conducting rod. Now, when the charges stop moving, that means that in that electric field, there's no charges moving, but it's still moving within the magnetic field. That means that the electrostatic force on those charges is going to equal the magnetic force, much like we saw in our mass spectrometer when we ionized the particles and sent them through the combined electric field and magnetic field. So if we look, the electric force equal to the magnetic force, and we can calculate the electric force. If you remember, that is just the electric field times the charge, and the magnetic force is just the charge times the speed times the magnetic field. So we have this equation, and we know that the Q values are going to be the same, so we can cancel out the Q values. And what we're trying to find is the EMF, or the change in potential between the ends of the rod. So remember that change in potential based on electric field is just the electric field times the distance between the charge plates. In this case, the charge ends of the rod. So that delta R is just going to be the length of the rod. So we can substitute in delta V is equal to the electric field times L. So that means we can multiply the other side by L as well, and we get that the induced EMF is going to be V times L times the strength of that magnetic field. And this is how we can calculate the motional EMF within that conducting rod. Now let's look at a separate example with a rod moving through a magnetic field, but this time we have that conducting rod along two parallel plates that are connected by a resistor. So the rod has a length of L, and what we're going to do is we're going to move this rod down the conducting plates to the right, which is going to induce a current pointing to the right, because what's happening is we're increasing the magnetic flux by increasing the area. So increasing the flux into the page means that they're is a change in flux coming out of the page from the coils of wire, which means if you take your fingers and point them from inside the wire out and do the grip rule, that means at the bottom, you're going to have your fingers coming and wrapping around on the bottom with your thumb pointing to the right, which gives us a current that is moving counterclockwise through this coil of wire. Now, in order to have it move at a constant velocity, we're going to have an applied force to the right, which means there has to be a magnetic force to the left. And if you use your right-hand rule for force, your thumb is going to be pointing up along the current pointing along the rod, your fingers into the page, and your palm is going to be pointing to the left, which is the direction of the magnetic force. So the applied force and magnetic force have to be equal to have a constant velocity, and that rod moves a distance of delta x into the field. And the flux, remember, is magnetic field times the cross-sectional area. Well, that cross-sectional area is just going to be L times x. So we can calculate the magnetic flux by doing BL delta x. Now, the motional EMF is going to be the absolute value of the EMF is going to equal the magnetic flux divided by the change in time. Substituting flux is BL delta x. We know that delta x over delta t, well, that's just the velocity of the rod because the rod's moving at a constant speed. So the motional EMF can be calculated by taking the magnetic field times the length of the rod times the speed of the rod as it's moving through that magnetic field. Now, using Ohm's law, I is equal to the induced EMF divided by R. We know that the induced EMF is just BL times V, so the current's just going to be BLV divided by R. Now, looking at our final example in this video, we have a conductor that has a length of 0.5 meters, and it moves at a constant 3 meters per second through a magnetic field that's perpendicular to the direction of motion and has a strength of 5 Tesla directed into the page. Now, the conductor is part of a closed circuit with a resistance of 2 ohms. And we want to know what is the magnitude and direction of the applied force to move the conductor in the field. So the first thing that we're going to do is we're going to mark our diagram with the things we know, keeping in mind that the magnetic field is 5 Tesla. And what we need to do first is we're going to use our right-hand rule to find the direction of the current in the circuit. So if it's moving to the right and the magnetic field is into the page, our thumb points to the right, fingers into the page, our palm points up, which means there's a magnetic force moving charge up along that rod. That's one way we can find the direction of current, or we can use the increase in flux is increasing into the page. So that means we have an induced magnetic field coming out of the page. So if we point our fingers out of the page and wrap our fingers around, the current's going to point to the right along the bottom, which means we have a counterclockwise current moving through this circuit. Now, second, we're going to use the right-hand rule again to find the direction of the magnetic force on our conductor. So the charge is moving up along the rod. The current is moving along the rod. So we point our thumb up, our fingers into the page. So that means our palm is facing to the left, and the magnetic force is going to be pointing to the left. Because the magnetic force is left, the applied force to the right, and it's moving at a constant speed, that means the magnetic force and applied force are going to be equal. So we found the direction of the applied force, that's to the right. Now let's find the magnitude of that applied force. Now, what we know is that the rod is now acting like a current-carrying wire. So the magnetic force is just going to be a force acting on a current-carrying wire, which is ILB sine theta. So the applied force is equal to ILB sine theta. Well, we know that the current and the magnetic field are perpendicular to each other, so theta is going to be 90, so sine of 90 is 1. So all we have to do is do I times L times B, and I, we're going to use Ohm's law, and we know that I is equal to the induced EMF divided by R, which is going to be BLV divided by R. So we can substitute that in for our current value, and then we can simplify our equation. We have L squared and B squared. When we simplify that, then what we can do is substitute all of our numbers in, and we can calculate and find that we have to apply 9.375 newtons of force in order to move this bar at a speed of 3 meters per second at a constant speed, and that's going to induce a current and an EMF in that circuit with our 2 ohm resistor. So this is an introduction to electromagnetic induction, Faraday's law, Lenz's law, magnetic flux, and motional EMF. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.